Hi everyone, this is lesson 2.2.1 of the transformations chapter, and in this lesson we're going to talk about stretches. Now before we begin looking at questions, it's important to know a couple things about stretches. First of all, stretches are always with respect to an axis, and as a result, they're the result of multiplication. So objects or points on the graph are either going to move away from or towards an axis as a result of multiplication. Often the issue here is that people get confused as to whether they are reciprocating to get the stretch factor or not. Now, to determine the proper stretch factor, consider the operations that would be required to isolate that specific variable that you're working with. This is just exactly the same way we did it with the translations. The question is, what do you have to do to isolate the variable? So if you have to multiply by a specific value to isolate the variable, then that value that you multiplied by, that's your stretch factor. Now, don't worry if you find that a bit confusing. We're going to do lots of examples where we'll discuss that. The last thing I want you to notice here is that the invariant points for a horizontal stretch are on the y-axis. Horizontal stretches are either going to be away from or towards that y-axis that's in the center. And the invariant points for a vertical stretch are going to be on the x-axis. In the same way, vertical stretches are going to take points and move them either away from or towards the x-axis. Now let's take a look at our first example. It says, given the function f of x is equal to x minus 3 squared plus 8, write the equation of the transformed function if f of x is stretched about the x-axis by a factor of 1 over 5. Now, first and foremost, we have to decide what direction this is going in. If it's being stretched about the x-axis, then we know that it's got to be a vertical stretch. And that takes a little bit of getting used to, but that's the way that works. Now I want you to think carefully about how this is going to affect the y variable in the equation. Okay, because we're going to isolate the y variable typically, what we're going to end up having to do is multiply through that by that vertical stretch. So the vertical stretch is going to move over to the other side of the function, and we are going to multiply through by 1/5 to make that happen. So our new function, g of x, will be written as g of x is equal to 1/5 f of x. We've already moved the stretch over to the other side of the equation. And now to finish this question, we will replace f of x with the function. And remember that since there are two terms in the function f of x, that coefficient up front, that 1/5, has to be distributed to both terms. And so we get 1/5 x minus 3 squared plus 8/5. Now this next question asks us to write the equation of the function f of x if it's being stretched about the y-axis by a factor of 3. And just like we did in the last question, our priority here is first of all to determine what direction this is. Because it's stretched about the y-axis, we know that this has to be a horizontal stretch. So it's the x coordinate, or sorry, the x variable that's being adjusted. Now, since it's the case that we don't normally isolate the x variable, when we put it into the function, we're going to need to reciprocate it. Uh, because normally you would multiply by the actual stretch factor to isolate the x here. But in this case, we're not going to do that. So we have to leave it the way it would sit there originally, and that means it has to be reciprocated in the function. So this means that in the g of x function, we're going to multiply 1/3 by the x, so it becomes f of 1/3 x. And then we can put that into the function f of x by simply putting a coefficient of 1/3 in where the x was inside the function. Now I'd love to tell you that that's as far as you need to go in this question, but we do, however, need to take this a bit further. So at this point, this is where we've gotten. We know that there was a horizontal stretch by a factor of 3, which meant we had to put a 1/3 in front of the independent variable there. And that's where we get g of x is equal to 1/3 x minus 3 all squared plus 8. That, however, is not the standard way to write the equation of a parabola. So what we need to do is factor that 1/3 out of those two terms in that binomial there. And so when we factor it out, now remember, I'm not taking it out of the square. I'm factoring out of the two terms within the square. So this becomes parentheses 1/3 times x minus 9. Then I've got two sets of parentheses there because, again, I haven't taken the 1/3 out of the square yet. So that's all squared with a plus 8 at the end. And now the last thing we'll do to finish this question will be to apply that square to the two factors within. And in this case, we're just going to leave it on the x minus 9 squared, but we'll take that 1/3 and square it because we know what that value is to be 1/9. And so our final result is 1/9 of x minus 9 squared plus 8. In this next example, we're given the graph of y equals f of x, and notice it's kind of an awkward function. There's not a nice simple equation for it. And we're asked to sketch the graphs of g of x is equal to 3f of x, and h of x is equal to f of 4x. And once we're done that, we need to state the domain, range, and the number of invariant points for both the transformations. Now, for this particular problem, it helps to find specific points that would make it easy to sketch when we transform those points. And so what I've done here is I've listed off the coordinates of all of the important points, all of those vertices or the endpoints of the line segments that make this graph up. Now, the easiest approach to this problem is to identify the mapping and find the image of each point and then to plot each point. So for this first one, g of x is equal to 3 f of x, this is because that 3 is a coefficient of the function, and that whole function there represents the dependent variable, this is a vertical stretch. The dependent variable on the g of x has been isolated, so this is a vertical stretch by a factor of 3. So our mapping is going to be x comma y maps to the point x comma 3y. So now, for each point, we simply multiply the y-coordinate by 3. So the 2 becomes a 6, the negative 2 becomes negative 6, 3 becomes 9, negative 1 becomes negative 3, and 2 becomes 6. All of the x-coordinates stay the same. And what you're seeing on the right there is the resulting graph. And you can see from there that it's now 3 times larger, although it hasn't moved horizontally. And in fact, notice that the invariant points, or the points that didn't change, were the points that cross the x-axis. Now with the graph, we can identify the domain and range of the diagram that we sketched. And it's pretty easy to see from our diagram that the domain will be from negative 6 out to 8 inclusive, and that our range is going to be from negative 6 to 9 inclusive, and that's the part of the function that changed. And since this is a vertical stretch, the invariant points are on the x-axis, as we just said before, and thus we're going to see that there are 4 invariant points in this transformation. Now let's take a look at the second transformation, and we're going to identify the mapping once again. In this case, this was a horizontal stretch. We've got the 4 multiplied by the independent variable in the function. If you were going to isolate that x, you would have to divide both sides by 4. So that becomes our stretch factor. So this is a horizontal stretch by a factor of a quarter. So that means in our mapping, what we just said, the description I just gave of the transformation is exactly what we see on the point. I'm going to multiply the x-coordinate by a quarter, and then the y-coordinate will stay the same. And so now we see that we just multiply each x-coordinate of every point by a quarter. So now our x-coordinates become negative 3 halves, okay? Negative 4 becomes negative 1, 0 just stays at 0, 2 becomes a half, and 8 becomes 2. And now when we take all of those new points and plot them, you can see the graph on the right. There's our new graph. And notice that it hasn't changed vertically from the original, but it has certainly gotten a lot narrower, okay, horizontally as compared to the original function. And once again, we need to identify the domain and range from the diagram that we just sketched. And in this case, we can see that the domain goes from negative 3 halves out to 2 inclusive. And the range is the one that doesn't change. It's going to go from negative 2 to 3 inclusive. And since this is a horizontal stretch, the invariant points are going to be on the y-axis. And thus, you can see from the original and from the result that there is only one invariant point in this transformation. This next example tells us that the graph of f of x is equal to x plus 1 squared plus 2. And it has been transformed to the graph of g of x by a vertical stretch factor. If the point 3, 54 is a point on g of x, determine the value of the vertical stretch. To answer this question, I think the easiest thing to do is just to begin by applying an unknown vertical stretch factor, and then using the information that we have to figure out what that factor must have been. And so in this case, we get that g of x is equal to a times f of x, which becomes g of x equals a times, and we put the entire function f of x inside there, so x plus 1 squared plus 2. This is all multiplied by a. Now that we have the general form of the function g of x, we simply need to substitute in that point that we know is on that function to figure out what the transformation is. So we know that g of 3 is going to equal a times 3 plus 1 squared plus 2. That's just function notation. But we also know that g of 3 has to be 54. On the right-hand side, then that 3 plus 1 becomes 4, which will be squared plus 2. 4 squared plus 2 is going to be 18, so 54 is equal to a times 18. And by a quick division, we see that a is equal to 3. Thus, the vertical stretch is a stretch by a factor of 3. This next example says that the function f of x has been transformed to get g of x is equal to a times f of bx. And we're supposed to determine the values of a and b for each of the following. So here's our first scenario here. There's been a vertical stretch by a factor of 1/3 about the x-axis and a horizontal stretch by a factor of 4/5 about the y-axis. This question is really just about interpretation. It's about going from the information that we're given back to the function itself. Since there has been a vertical stretch by a factor of 1/3, that means that in order to get the y by itself, we would have had to have multiplied both sides by 1/3, and so the value of a, which is in front of the function, has to be 1/3. And since we don't typically solve for x, when we're told that the horizontal stretch is by a factor of 4/5, now remember, that's the number that you would multiply to get x by itself. So in this case, what we're seeing in the equation must be the reciprocal of that, and so we know that the value of b must be 5/4. And now part B of this question says that there's been a vertical stretch by a factor of 2 about the x-axis and a horizontal stretch by a factor of 8 about the y-axis. And once again, this question is really just about interpreting the transformations and putting them in the function. And now we'll start to do this a little quicker. Since there's been a vertical stretch by a factor of 2, that means the value of a is 2. And since the horizontal stretch was by a factor of 8, we know that this means that the value of b must be the reciprocal of that, 1/8. Okay, now this next question is similar to the one that we just did. We're going to write the functions representing the image of, and in this case it's y equals the absolute value of x, after a vertical stretch by a factor of 4 and a horizontal stretch by a factor of 3/2. And now hopefully at this point you've noticed the pattern here, that all we have to do is really remember that we have to reciprocate the horizontal stretch factor when we put it in the function. But we don't need to do that with the vertical stretch factor as long as we are putting it on the other side of the equation away from the y. So as long as it shows up in front of the function, the f of x, we don't need to reciprocate it. So we can quickly write the transform function as y equals 4 times the absolute value of 2/3 x. And now notice that this can be simplified to y equals 8/3 of the absolute value of x. Because the coefficient there isn't going to affect the sign of the x there, the absolute value is not going to have an impact. I can just factor that right out. I do apologize that that value is at the very bottom of the screen there. And now in this next question, we're going to write the image of y equals the square root of x plus 2 after a vertical stretch by a factor of 2/3 and a horizontal stretch by a factor of 1/2. And as we go through these problems, I hope you're seeing the issues that are popping up. As before, we need to remember to reciprocate the horizontal stretch factor. So that's the issue with horizontal stretches. But we also need to remember to distribute the vertical stretch factor through the entire function. And that is the issue for the vertical stretch. So symbolically, we can quickly write that g of x has got to equal 2/3 of the entire function, the square root of 2x, we reciprocated the horizontal stretch, plus 2, all in brackets there. And then we're going to distribute the vertical stretch to get 2/3 of the root of 2x plus 4/3. Now in this question, we're going to look at things in a little different way here. I want you to state the transformations that take the first function to the second function written below. So this first question, we're going to look at and compare the functions y equals 4 to the x to 3y is equal to 4 to the 5x. Now the first thing you might notice is that the y was replaced with 3y. And so in order to isolate the y, we'd have to divide by 3, which we know means that the vertical stretch has been by a factor of 1/3. And likewise, notice that if you were to solve for x, the last thing that you would do would be to divide by 5, unless we consider there's been a horizontal stretch by a factor of 1/5. And now let's compare the two functions y equals x squared and y equals 4x squared. Now this is a really interesting question because it can be interpreted in two different ways. On the one hand, and I think arguably probably the most common way to see this, is that we see this as a 4 being multiplied by the original function, and that would obviously then make this a vertical stretch by a factor of 4. On the other hand, you could interpret this as the x variable being replaced by 2x. Because when you do that, now notice that x is being squared, so if we replace x with 2x, that would mean that the 2x would be squared, and when you distribute that square to the 2, you would get that 4x squared. Now, the resulting equation is the same, transform function is the same, But in this case, the way we're interpreting it, we would get a horizontal stretch by a factor of 1/2. Now, because we're getting the same equation regardless, what this means is that these two are visually exactly the same. Not only are they algebraically the same, they're visually the same. Now let's take a look at a pretty straightforward question here. We're going to compare y equals the absolute value of x to y equals 2/5 of the absolute value of 6/7 x. And you can probably tell by looking at it that there's been no real big effort made to hide the stretches here. Because the 2/5 is outside the function, it's the coefficient outside the function, we know that there's been a vertical stretch by a factor of 2/5. And since 6/7 is within the function as a coefficient of x, there's been a horizontal stretch by a factor of 7/6. Now let's identify the transformations that take y equals x cubed to 1/2 y equals 3x all cubed. And in this case here, to identify the vertical stretch, we should first isolate the y variable. It's not absolutely necessary, but it's a pattern that I'm trying to establish with people. And when we do isolate y, we get that y is equal to 2 times 3x all cubed. And once it's in this form, the stretches become fairly obvious. Since we had to multiply by 2 to get that coefficient of the y over to the other side of the function, we know that there's been a vertical stretch by a factor of 2. We can also see that because there's a 2 outside the function. And since we see that there was a 3 inside the function as the coefficient of the x, we know that that means there's been a horizontal stretch by a factor of 1/3. And again, you can see that if you think about what you would have to do to isolate that x. You would have to divide by 3. And again, that means that that's the stretch factor. Now, the difference in this next example is that the question is going to be asked with reference to a graph. So in this graph that you're seeing below, the thick line is the graph of the original function y equals f of x, and the thin line is the graph of the transformed function y equals g of x. And what we want to do is, based on the graphs that we're seeing here, we want to write an equation for the transformed graph g of x in terms of f of x. Okay. The assumption here is that we don't exactly know what the type of function is. We're assuming it's probably a parabola, so it's a quadratic, but that's not necessarily true. Now, it's important to make the following assumption. Since we're in the chapter when we're talking about stretches here, you have to assume in this case that the only transformations that have occurred have been stretches. You might argue that you're seeing translations here, but because of where this question is showing up, the proper assumption is that these are just stretches here. Now, in this case, the easiest way to pick out the transformations or the stretches here is to pick a point that has clearly been transformed. And because this looks like a parabola, let's just kind of assume at this point that that is the function here. So with a parabola, the point that you're normally going to choose is going to be the vertex. And now, since stretches are with respect to the different axes, all we need to do is compare the distances that the vertex is to the different axes. So in this case, it's moved from 4 units below the x-axis to just 1 unit below the x-axis. So that means there's been a vertical stretch by a factor of 1/4, because that distance 4 has been multiplied by 1/4 to get 1. And then we can see that it's been moved from 4 units to the right of the y-axis to just 2 units to the right, and thus there's been a horizontal stretch by a factor of 1/2. Okay, now this next question tells us to determine the zeros and the y-intercept of the polynomial function p of x is equal to x minus 2 times x minus 1 squared after it's been transformed such that, and the first one we're going to look at here is y equals 6 times p of x. Now I think clearly the first thing we have to do is ignore that transformed function. We've got to look at the original function and determine the zeros and the y-intercepts. So because it's factored, it's quite clear that the zeros would have to be 2 and 1. Just think back to how you solved equations even in Math 20. And then to get the y-intercept, all you got to do is substitute in a 0 in for the x variable in the polynomial, and you'll see right away that the y-intercept is -2. And now we consider the transformation. In this case, it's a vertical stretch by a factor of 6, and that is only going to affect the y-intercept, not the zeros. Anything on the x-axis is going to be invariant under a vertical stretch. So the zeros will remain 2 and 1, but the y-intercept is going to become -12. We're going to multiply that 2 by that -2 by the 6. Okay, and now this next transformation we're going to look at is going to come from the polynomial y is equal to p at 3 of x. And I apologize, this should be labeled as question B, but it's not, it's a mistake. Now in this question, it should be pretty clear that there's been a horizontal stretch. And again, think about what you would do to isolate the x. You'd have to divide by 3, so there's your horizontal stretch factor by 1/3. And this is going to affect the zeros, but not the y-intercept. Anything that's on the y-axis will be invariant under a horizontal stretch. So this means that our x-intercepts here, our zeros, will end up becoming 2/3 and 1/3. We just multiply each of those by a third. Now, I apologize for this. That y-intercept should have been just -2, not -12. That's a cut and paste problem that's my mistake. I apologize for that. That should have stayed -2. Now, for this next transformation, the only difference here is that now it's still a vertical stretch. You can see that because it's 1/2 in front of the p of x. It's just going to be a fraction as opposed to an integer stretch. And remember, just like in question A, this is only going to affect the y-intercept, not the zeros of the original function. Okay, and as I look through the work that I've done, this is an embarrassing series of mistakes here. The new y-intercept here should not be -6. It should, in fact, be just -1. The original y-intercept was -2. There's going to be a stretch by a factor of 1/2 that takes it down to -1. And the zeros are going to remain unchanged at 2 and 1. Now finally, let's take a look at one more transformation where y is equal to p of 3/8 of x. And in this case, it's just like it was in the previous question where we had a horizontal stretch. In this case, it's going to be by a factor of 8/3, which is what makes this one a little different, just a fraction there. And it's only going to affect the zeros, not the y-intercept. And so we multiply our zeros by 8/3 to get 16/3 and 8/3. And the y-intercept, now again, that mistake is persisting here. It's not -12. The y-intercept is in fact just -2.